All right, so with homework, I had recorded a video yesterday, like right, I don't know, 11:30 or something, before a normal class, but just going through how to set up two equations, how to recognize, like, once you have two equations, two unknowns, how to go through that. There's more than one way to do it. I like linear algebra because it's pretty extensible. If it turns into 5 equations, 5 unknowns, it's still the same process. Identify what I know, identify what I don't know, and then have either computer or calculator solve problem for me. If you solve for one, plug it into the next, then go back, really you're doing like a back and forth Gaussian elimination, which is a linear algebra process, but yeah, 6 of one, half dozen another. You'll get there. So that's what I did. Then also someone reached out to say, hey, the second problem doesn't make any sense. I'm like, sure it does. It makes total sense. But I think the position of this link B was in the wrong location for the second part. Did anyone notice that? Yes? Yeah. Did anyone else notice? The link, like the hinge B, was in the wrong spot, so that if you went from O to A to B to C, it did not add up to the 0.25 plus 1. It wasn't 2.25 meters. It was, I don't know, something else, something that was not 2.25 meters. So it broke the actual linkage system. So I went in and I fixed it. Position of B should have been 1 meter over and 25 centimeters up. If you solved it and you just said, like, this is it, I mean, you did the best with the information you had, it's okay. But if it was bothering you, that's why it was in the wrong location. Yeah.
The thing that I was confused about with problem 3 was problem 3 on the source, right?
Yeah.
The thing that I was confused about was what exactly is asking me to find out. Because on the bottom it says what the rotation rate is 3.
Yes.
And what do you mean by rotation rate? Because I think that means as how long does it take for it to go back into the position.
That would be average. That would be, so if you figure out like how long it takes for one cycle, that would be the average rotation, or the average kind of cycle, which has to be 10 radians per second, or whatever.
Rotation rate would be...
That one's an instantaneous, like how fast is the thing rotating?
Okay.
Yeah, like kind of like what is the speedometer on rotation? That's rotation rate. So and that's why when I was solving this specifically, I was saying, like, what is theta 2 dot? What is theta 3 dot? Because that's telling me rotation rate of link number 2, rotation rate link number 3. Yep. Okay. Using formulas. L3 is 1.25. Oh, in the... Oh, that L2 was the wrong length. That's fine. I mean, as long as you have like this is my engineering work. This is what I can do with what I have. I think that would have worked. But here's like the actual, this should have been the real location of hinge B, 1 meter, 25 centimeter. Other questions on, because I didn't actually entertain questions on Monday when I was just like da, 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 just talking to myself in my office. Yeah.
It's not with homework. The project's due on Thursday, right?
Project probably Thursday based on how it was scheduled a month and a half ago, but we're not going to finish it. Yeah, we're not going to finish that, so we got to push that one at least till Monday, so we can have Friday afternoon to open it up, take a look at it. Yeah, project. We got to move project back. Yeah, because the project, and we still need to work on quiz number 2, like building that one today. That one was supposed to be due tomorrow. Maybe we'll push that till Friday, at least Friday. Give us like 48 hours to process it, and then work on project 2. Cool. All right, first step is, what was module 2 about? What kind of concepts or skills did we need for it? And then next step, how do you actually demonstrate that you can do those?
It's a very
That's an interesting topic. I wouldn't mind. And they came up with innovation. Like personality modified.
But it's not one function. It's a couple. I mean, technically,
Very human solve that have a function, and then a function that you can actually solve coefficients of it. It's two that have it.
Yeah.
like invert the matrix. I guess you can invert the matrix.
It's a little wonky. I think that kind of getting it.
I think $50 a share.
Okay. Yeah. Yeah, but the main thing is like. Yep. Well, I mean, probably one of them.
Yeah.
Yeah.
$130 a share. What's it called when it's like INJ? Linear algebra? No. There's like linear systems class. Yeah.
All right, I'm just jotting down some quick things. So one thing that came up was like we were doing statics and force balance here. I mean, why did we need that in a dynamics class? Shouldn't everything be non-static? Everything's moving. Like we didn't look at any problem where things were static. Why did we use kind of no? Because when we said there was like a force balance, sometimes or some of the forces equaled 0, even though stuff was moving. Why is that? We had like a specific term for that one. A quasi-static analysis. So somehow your like change in momentum is still 0, even though the thing is moving. Like a quasi-static. Then we had like degrees of freedom and constraints. What do constraints do to degrees of freedom? Yeah. Yeah, so if you have all these moving parts and you start hooking them all together, then you reduce total like system degrees of freedom. Each part might have whatever, it's 6 degrees of freedom, but then when you pin it into place and now it's a door swinging on a hinge, it only has 1 degree of freedom. It can only rotate around that one hinge. So every time we add a constraint, we remove degree of freedom. The fancy word for that, maybe not fancy, the silly word, Grubler. Sounds like something from Rick and Morty, but the Grubler count is like total like number of parts and their degrees of freedom. So every part has 6 degrees of freedom minus all the constraints. So like it would be 6 times number of parts minus number of constraints. So at least in 3 dimensions. If you're only talking 2-dimensional, then it's 3 times. And I know we didn't like specifically talk. We talked about degrees of freedom and how to like understand what they are and kind of get a sense of what that means. Grubler count is the way to sort of calculate that. And that's what like dynamics, if you have like a software that's doing dynamic analysis, it can calculate the Grubler count for you, but it can't calculate degrees of freedom of the system, because all it can do is add up like how many parts are there and how many constraints did you add to it. So sometimes Grubler count is negative. How would that happen? What is it? Could be over-constrained. What if it's negative, but it can still move? Yeah.
Maybe you can move like along with something, but it itself can't move its position.
Might not move in its position.
Well,
Yeah.
together, but it's
So like one example of a Grubler count that's negative is like when you put a hinge on something, you create 5 constraints, because one hinge on a door, it can only rotate around the hinge. So you took 6 degrees of freedom, turned it into 1. If you put a hinge on the top of the door and the bottom of the door, according to math, 6 minus 5 minus 5 is now -4. But the second hinge is the same constraints as the first hinge. So negative Grubler count usually means you're like creating the same constraints more than once. Here, we don't have to deal with it too much, but what other things came up? What else? There's one suggestion that there was no calculus in this part. Did we use calculus at all? Where did it come up? Rate of rotation. Where did that come up? Why did we need calculus? Because for a lot of this we didn't. For anything that's quasi-static, you do not need calculus. Absolutely not. Like it's all kind of direct force balances and that kind of stuff. And even degrees of freedom and constraints, usually not. Like you don't need calculus to figure that out. Yeah.
We're using like integrals and derivatives.
Would we use, integral, what was integrals, derivatives? What was that one?
Like with the unit vectors.
The unit vectors. Yeah, did we need integrals for unit vectors? Yeah, I like the, something like, yeah, so like we have a very specific definition of like velocity is a change in position. So when we create constraints on position, if we take a derivative of that, it has to satisfy the same constraints. And that's where like those ideas of like whether we go from velocity to position or position to velocity, we need like some kind of like integral or derivative. So like so we had that if we could create like vectors to describe like, okay, this is how position doesn't change. Like some things in here are changing, other positions are not. We did like a vector loop to figure out that 4-bar linkage. We could do other vector loops or things, but once you have position, you take a derivative. Now you also have constraints on velocity. You could do another one, find constraints on acceleration, but that was where like calculus mainly came in, purely in like the kinematics. Like we weren't really dealing with like differential equations, not in the sense of like this the change in this velocity is equal to velocity and those kind of things. It was more like direct application of like, this is my definition for velocity in terms of position. These are all the abstract concepts and skills. At least it seems like we hit most of them. Did I miss anything? All our like critical thinking kind of work. I think we did a pretty good job. All right, so then the next part is, what questions could we use to like demonstrate that we know how to do this stuff? We know how to either do a quasi-static analysis, or maybe a quasi-static and understand constraints on a problem, something like that. So what could we do here? What kind of questions would demonstrate that on a quiz, on any of these? Either a combination of them or one in particular. That's what we're trying to figure out. No?
No,
Oh, okay. It's like just no. I'm not going to do it. If you're moving, this is what it takes capacity.
should show that we were.
If you lock one, it should mean that all
You want to see?
you can. All rotation rates go to 0. Because if you think about like keep one at one or
Like, so this is like the one that we have. So like it says like I get a consistent speed.
so if you said like theta 1 can only be 4 to 5, theta 2 and theta 3 are always the same. Yeah. You're right. Let's say we have a bike, it's moving at a constant speed. How fast are you pedaling? Do we need like force balance for this? Do we need to figure out like how hard we're pushing on the pedals? Like how much torque there is? Maybe? Why is that? Yeah. Yeah. But if we know we're going at, let's say we're moving 10 miles an hour, nice party pace. So we're not accelerating, we're not decelerating. Okay, so yeah, gear ratio. What is gear ratio really telling us? Is that like a force balance problem? Like what is? Yeah.
Well, gear ratio impacts like the torque or the top speed of the object.
Okay. Why does it affect top speed?
Because an object with a smaller gear ratio, the gear can spin much quicker, right?
Okay.
Per one spin of the gear attached to the system.
Okay, so if you're pedaling a bike and you want to go fast, what do you want? Large gear ratio or small gear ratio?
Small gear ratio.
Small? Small gear ratio. So like up front, like, so we'll say 1-to-1 versus like 10-to-1, like 10 teeth to 1 tooth. I mean, really, it would be like 10 to 100. Like that would be an insane cassette up front. So which one is faster, 1-to-1 or 10-to-1? Yeah. 10-to-1? Okay, so yeah, like you move your foot around 1 rotation, we get 10 wheel rotations. That's moving pretty darn fast. Usually like max is sort of like maybe 5-to-1. 10-to-1 is insane, that would be. But we would definitely 10 to 1, you'd be moving very fast. But what's the assumption here? Like, we're saying one is faster than the other, but but we're implicitly assuming something that I'm not sure anyone. One, that your legs are strong enough. That's one part. Let's say, I mean, here, like, sooner or later, with just a constant torque, you'll get up to speed, right? Like, if torque is constant, you might be moving it like stressing to start, but sooner or later, both of them will get to a constant speed. Or we're making an assumption here. What is that?
Similar angular velocity.
Angular velocity? What about it?
The speed of the rotation has to be the same.
That the speed, okay, yeah. So what we're kind of saying here is that for a normal person pedaling at a normal speed, you will move much faster with a 10 to 1 gear ratio. A normal person pedaling at a normal speed at 1 to 1 is moving very slowly. That's kind of like hill climbing is a 1 to 1. And the reason for that is, like, we as people can really only do maybe 2 rotations per second. It gets really hard to do like 5 or 6 rotation, like pedaling 5 or 6 times every second, right? Because now your feet are moving so fast, you can't actually put any power down. Have you ever seen like dynamometers for engines? Do you know what a dynamometer is? Have you heard of this? You have your RPM and your torque. There's some kind of, and I'm like just drawing, I don't like to draw graphs like hand drawing, but in general, every engine, even ourselves, we're like some kind of heat engine. We input food, we output heat and work. We have some kind of optimum RPM that we can really handle. So that's what the gear ratio is doing for you, is like keeping the bike at your optimum gear ratio level. So you pedal at a comfortable speed, your bike moves at a good speed. Yeah.
What is the
Torque. So dynamometers, usually it's kind of like the faster you run your engine, the more power you get out of it. But there's an optimum, like at a given RPM, you'll get the most torque out of your engine. For diesel engines, it's much lower. For gasoline engines, it's a little higher. Electric engines, super low. They have like tons of low-end torque. So low RPM electric engines, that's what you want to do. So you create gear ratios in order to get the wheels to move at a different speed. Anyway, that was a long explanation for like, it's all, this kind of question is like, it's all kinematics. Like, we're just looking at what is the geometry of motion of moving a bike. And then the other things that come with that might be like a quasi-static analysis of like, okay, here are the loads on the bike, how much power are we putting into it or something. Yeah.
Do you know what is the ratio in in the vehicle, the cars or the boats? What that ratio can be?
So cars and motorcycles actually flip. So and there was a senior design team working on like creating a different type of transmission for a bicycle. And what they were finding was like the amount of torque that a person actually puts more torque on the drivetrain than a car does, a car or a motorcycle. But a person can only create like 2 rotations per second. Meanwhile, a car is creating like, 6,000 rotations per minute is 600 rotations per second. That 6,000 is too high, but kind of get the point. So like 300 rotations per second. So you get a lot more power out of a car, but it's similar torque values, even though you're...
How about boats?
Oh, for boats? Boats usually don't need like gear ratios on boat, like you can just sort of design the propeller. Like the propeller is kind of your gear. So depending on what angle you put the propeller at. So usually boats are just kind of like more power is just faster, like spin it faster. You don't necessarily need to like gear it up or down, versus a car. If your wheels were spinning at 3,000 rotations per minute, you'd be doing I don't know, pretty fast. I don't even know offhand, but very fast. So usually it's geared down by a lot. Like I think rather than a 10 to 1, I think it's like a 1 to 10 or a 1 to 20, something like that. So you have a real small gear on your engine and a real big gear on your wheel, or on the rest of the drivetrain. And you see that with motorcycles, they're kind of flipped. They have a small gear up front and then a big cog on the back of the motorcycle. And scooters, same thing, big cog on the back, little thing in the front. Yeah. This was fun. But, oh no, we're running out of time. All right, so what would you do here? So let's say we know the gear ratio. 10 to 1 is kind of high. We'll say it's 5 to 1, right? For every 5 teeth, we have 1 tooth in the back. So maybe a 10 and a 50, something like that. Why does the gear ratio matter for how fast we're going? Yeah. Okay. How does rotation speed relate to forward motion? Yeah. Traction. Yep. So what is the constraint on the wheel motion and the forward motion? Yeah.
Sorry, maybe misunderstanding the question, but isn't the limitation how fast you can pedal? Like the RPM which you can pedal at, so you have to change the gear ratio so that the motion of your feet on the pedals matches more the rotation. Sorry if that explains this well, but
no,
as the wheel of the bike is spinning faster, you gear up because otherwise you would have to pedal equally as fast.
Yes. Yeah. So like with a 1 to 1 gear ratio, you need to pedal very quickly to maintain, let's say we're moving 10 miles an hour. So 10 miles an hour, what is that? 5 point something meters per second. So yeah, gear ratio definitely matters for how fast we need to pedal. But if we fix the gear ratio and just say like, all right, the bike is moving this fast, how fast are we pedaling? What is the connection between speed and rotation? Like how fast is the wheel rotating if we're moving 10 miles an hour? This one we need some kind of constraint, right? Like we know it's kind of 1 degree of freedom. If we move forward, the wheel's got to rotate. But how much did it rotate? Yeah. One rotation is 1 circumference. Yeah. So like, let's say we moved half, or 90 degree, pi over 2. 90 degrees. Do you know how far we went? It'd be like a piece of the circumference, right? Like we're kind of tracing out the circumference onto a sheet of paper. Yeah. So now we have like r pi over 2, or in general, if this whole thing is theta, this distance is r theta. So the amount that we rotate is the distance we travel. So it gives it, now we have like a constraint equation on rotation and motion. The more we rotate, the further we go. Okay. So then how fast are we going? Divide by time? Yeah. So r theta over a delta t? Yeah. What happens if we take the limit of delta t goes to 0? Goes to 0? So we're not moving. Motion is impossible. Goes to infinity. So you can't move. You either move 0 or infinity. That's always the answer, right? 0 or infinity. What's the ddt of r theta? Is the radius changing? No? What about theta? Has a rate, right? So forward motion is our r theta dot. Like, remember, like once we have a constraint, like distance is r theta, we can take a derivative. The change in distance is velocity, so the change in distance is r times d theta dt. So it's the same kind of process here. Like if we know, and now if we know radius, we know gear ratio, we could say for this given speed, this is, and maybe we want to choose the gear ratio of like, I want to go this fast, and I want to pedal at this speed. What gear ratio do I need? That's like a solid sort of question, and it goes both ways. Whether you have like an engine, like I want my engine to do 3,200 RPM, or I have a body that wants to do 2 RP, like hertz. Sorry, question? No? Oh, for a distance in r theta? That one is like, for a given, so if you have a curve, if you want to find the length of the curve, r times the angle is that length, yeah? In radians, so it's got to be radians. Like r times 45 degrees is meaningless, but r times pi over 4 is an actual like distance. And if you do 2 pi, like a full rotation, now you just calculated circumference. How does this one, are we overtime? We're already overtime. How does this one feel for the quiz? I got fixated on it, sorry, but we're ready, feel prepared.